All right, guys, so welcome back for part two, where we're going to be graphing a system of inequalities. So today we're going to represent constraints by equations or inequalities, and then use those to graph and determine solutions for that system. So you're going to need a Springboard book today, something to write with, and your calculator handy. Okay, so we're on page 24 in your book. So we're starting where we left off with our first video. So yesterday we looked at feasible options for Roy. And remember, something is feasible. It just means that it's possible for a given situation. Okay. So yesterday we were talking about different options for Roy to spend his prize money. So we had we made this chart where we talked about, could he buy so many tickets and so many meals? Was that feasible? Meaning, was it under his budget of $1,360? Remember his leftover prize money after his hotel and taxi expenses. So when we talk about if something's feasible, it just means, is it an option for him and does it make sense for his situation? So yesterday we came up with this inequality and we graphed it where we had $100 per ticket plus $40 per meal. That has to be less than or equal to the money that he has to spend. Okay. So we had that equation yesterday that we graphed. So if we're picking up where we left off with number 11, it says Roy realized that some other conditions or constraints apply. Okay. Constraints just means that there are conditions or inequalities that limit a situation. So he has some other situations or conditions that he has to take into account about how he spends his prize money. So on A, it says Roy eats lunch and dinner on the first day. On the remaining 4 days, he eats at least one meal each day, but never eats more than 3 meals each day. So that's kind of wordy. So let's break it down just a little bit here. So let's talk about the first day. Okay, and how many meals he eats. So on the first day, it says he eats lunch and dinner. So we're going to count that as 2 meals. Okay. And then we have the least amount of meals he's going to have and the most amount of meals he's going to have. So let's look at that too. So the least amount of meals and the most amount of meals. Okay. So on the remaining 4 days, Roy eats at least 1 meal each day. So if he eats at least 1 meal each day for 4 days, that's a minimum of 4 meals for those 4 days, right? He has 1 a day for 4 days. But it says he never eats more than 3 meals each day. So if he has 4 days and he eats 3 meals for each day, what's at most then? How many would he have? Well, 3 times 4 would give me 12 meals. Okay, so on the first day he eats 2, and then the least amount of meals after that he would have is 4 if he just has 1 a day. The most amount he would have after that is 12 if he has 3 meals each day. Okay, so we're going to write an inequality here for our meals. We're going to kind of write it as a double inequality like this. Okay, so if we kind of read this from M, if I read this to the left, this is M is greater than or equal to. And then if I read it as we go to the right, it says M is less than or equal to. So we're kind of sandwiching M in the middle there. But let's think about the least amount of meals that Roy's going to have total. So for the 4 days, he's going to have 4 meals, but he has the 2 meals that he started with. So at least the least amount of meals he's going to have total is 6 meals. Okay. Now the most amount of meals he's going to have, so he's going to have the 2 from the first day, but on those remaining 4 days, that most he could have is 12 meals. So if I combine those, the most amount of meals he's going to have is 14. So we see a range here for his meals. He's going to have the least amount of meals he'll eat is 6. The most amount of meals he's going to have is 14 total for the 5 days he's there. So again, we count the first day because he's going to have lunch and dinner. So that's 2 meals. And then we look at the remaining 4 days So the least amount was 4, the most was 12. So combining those, we get this range of number of meals. Okay, so that's one constraint. Another constraint are about his performances. So there's only 10 performances playing that Roy actually wants to see while he's in New York City, but he may not be able to attend them all. Okay, so we're going to write a restraint now about the tickets. So it's going to kind of look similar to the meals, where we're going to have kind of a range from a low amount of tickets he's going to have to the max amount of tickets he's going to buy. So he says there's only 10 that he actually wants to see. So 10 would be the most tickets he's going to have. Well, what would be the least? The least would be if he attends no shows at all. Okay, so now we have, I'm going to get a highlighter here. We have these extra restraints. We have the meals restraints and a restraint on the tickets. Okay. All right, one more. It says Roy wants the number of meals he eats to be no more than twice the number of performances. So really quick, let's talk about what no more than means, because we have to translate that. Okay, so here's a little example. If your mom says you can have no more than 2 friends over at your house, well, that means you can have 2 or less, right? Because if you have more than that, she's going to be mad. So no more than is a symbol that means less than or equal to. Okay, so one's kind of a tricky one, but so let's write this. So he says he wants the number of meals, so I'm going to go M, to be no more than twice the number of performances he attends. So twice the performances, we were using T for that one, right? So that would be 2T. So that is our third constraint here that Roy has. Okay, so we have a restraint or a condition based on the number of meals he eats. We have one more condition about the tickets. And then finally, the one about the meals, how he wants to kind of balance his meals and his tickets. Okay, so we're going to take all of the inequalities we have now and we're going to graph them together. So we can use a graph to organize all of Roy's constraints when he goes to New York City. Okay, so it says to list all the inequalities from item 3 and item 11. So item 3 is what we did yesterday, that inequality that we have with 100T plus 40M is less than or equal to 1,360. Okay, and then 11 are the 3 restraints we just came up with. Okay, with his meals, his tickets, and the meals can be no more than 2 times the tickets he gets. So he wanted us to graph this on a grid. So I'm not actually going to do it by hand. I'm going to show you guys using Desmos. So I'm going to go and click this link here. So if you have to pause to kind of copy down all of our equations, then go ahead and do that. But I have these pre-graphed out for us already. So what we're going to do is look at all of them graphed on a single grid here. Okay, so here's the one we graphed yesterday. So it's kind of that triangle. I'm going to zoom in a little bit. Okay, where we had the meals, our X and our Y intercept to tell us our meals and our tickets. Okay, now in this case, X is representing the tickets. Okay, and axis is representing our meals. So I can't use M and T on Desmos. I can only use X and Y. So just make sure we remember that. Okay, and now I'm going to graph my other constraints with that. So remember, this is the meals. He's going to have on the low end 6 meals, but on the high end 14 meals that he's going to pay for. So I'm going to graph that there. So that's the orange one that just came up. Okay, for the shows, so X is our tickets here. We're talking about he can go to as little as 0 shows, but at most he's going to go to 10 shows. If I graph that, there's those boundaries. And then finally, he wanted his meals to be no more than twice the amount of tickets. So we're going to go ahead and graph that. Okay. So here are all 4 of our constraints graphed together. Now, if you had to guess, where do you think all of our solutions are going to lie on this graph? Okay. Well, hopefully you said our feasible solutions to match all of these constraints would have to be where all of the graphs overlap. Now, I can't really write on this, but it would be kind of in this section here if you just follow my cursor. Okay, kind of in that triangle-y shape here. That's where our constraints all overlap each other. So that's the only ordered pairs would be in this section where it would be feasible to kind of have all of these constraints met at once. So let's go back to our notes here in our book and answer the questions. For number 13, so it says, by looking at your graph, identify two ordered pairs that are feasible options to all of the inequalities. So I'm going to pull out this graph here and we're going to look at it. Blow it up a little bit, make it a little bigger. Okay, so looking at the graph, so again, tickets here on the x-axis, meals up the y-axis. So this is kind of a shrinked in version of what I just showed you, of where they all overlap each other, kind of in this weird shape. So give me an ordered pair that could be a feasible option for Roy that meets all of his constraints. Okay. Well, hopefully you picked something that was inside of this shaded area where all four of our constraints overlap each other. So for example, I could pick something like 6, 8. So Roy could go to 6 shows and eat 8 meals over the 5 days. Okay. Or another option, maybe we said 8, 12, meaning he went to 8 shows and had 12 meals. Okay. So label the point 6, 10 on our grid. So 6, 10 would be here, right? Interpret the meaning of this point. So we kind of just went through that a little bit. But 6, 10 means he's going to see 6 shows. So he's going to buy 6 tickets. And he's going to have 10 meals he's going to eat. Okay. So again, anything in this shaded area are feasible options, meaning they're good for Roy. And he's able to actually purchase those. He has enough money. Okay. So I'm going to end it there. So the big takeaway from today is making sure that we kind of can talk about when we have multiple constraints, meaning multiple inequalities. So the way we see where our answers lie is we graph them, and then we just look at where everything is shaded on our graph, okay? So that's all for today, and we'll practice more tomorrow. But doing our system, a system of linear inequalities means you have more than one inequality, and you're looking for that overlapping when you actually shade your graphs. And again, you can always use this Desmos where it can shade it for you. So all you have to do is know where to look. So you don't actually have to graph anything by hand if you have something that'll graph it for you. Okay? All right, guys, I'll see you on the next video. Thanks.